Okay, so our final example is Google's PageRank, and I'm going to talk about a simplification of it, which basically has all the right concepts, and in the next clip I'll kind of tell you the final ingredient that makes this almost good PageRank into to Google's PageRank. So before I kind of describe this very simple idea, what's our goal? So the idea is that when you go to Google and make a search, right, you're putting in a bunch of keywords, right, and based on those keywords you can get a list of web pages to display, right? So pretend that you're Google and your kind of customers are coming into your page and they're putting in some text into the search box and clicking enter, and your job is to give them a list, right, of relevant search entries, right? Basically a list of web pages that you think are relevant to their search. And the most obvious idea is to try to match the words, right, the search query, right, the actual phrase that was being searched for, to search through all of the web pages on the World Wide Web and match them, and then kind of once you find a good subset of pages that are candidates, right, basically pages that reflect the same keywords that you have entered or phrase that you entered. Once you have this list, the idea is what order do we actually present the list in, right? It's who gets the search results are ranked, right? There's search number 1, search number 2, search number 3, and usually kind of on the very first page, which has maybe the first 10 kind of results, usually you definitely find something relevant. Even though for any Google search you'll usually see like hundreds of thousands of results, right? Potentially relevant web pages, but the question is which one, who gets in the top 10, right? Who gets on the very first page of the Google search, and who gets the number 1 ranking, who gets the number 2 ranking, right? And so that's the idea of PageRank. By PageRank we mean how do you sort the from the list of pages that are match all of the right keywords. How do you sort those and present them to the person who is searching on Google? And so the way you do this is essentially through the stationary distribution. So I mean the punchline, you can almost stop watching the video here, but Google PageRank is the stationary distribution of a process that's happening on the World Wide Web. And so what you want to imagine here is take all of the web pages in the universe, or maybe on Earth, I guess. I don't know if there are any alien web pages out there, but maybe. But let's say we have n web pages, and what you want to do is construct this kind of it's essentially what this is you're constructing a directed network. And if you look at the original paper by, this is Larry Page and Sergey Brin, right? This is their Google paper was published in maybe 98 or 99. One component of it is this of the Google engine, so to speak, right? Is this web crawler that goes through all of the web pages on the internet and tries to determine who links to who, right? So we have which web page links to which other web page, right? So maybe New York Times links to the Washington Post, and the Washington Post links to, I don't know, some CNN or something, right? And so on. So one part of what Google does is crawls the web and records to get the most recent snapshot of who links to who on the World Wide Web, creating what is essentially a directed network, right? Directed. We'll talk about what I mean when I say directed in a minute. But that's kind of the first thing you want to imagine for yourself, and I'm encoding that in this matrix L, the entries of which are either 0 or 1. And so the ijth entry of the matrix L is going to be 1 when web page I links to web page J, right? So whenever there's a link from the New York Times to the Washington Post, in this case, New York Times is page I and Washington Post is page J. Whenever there's that link, I'm going to put a 1 there, okay, and 0 otherwise. Like the New York Times is not going to link, I don't know, some blog or something out there. Right? It's not going to have a link to some random guy's blog. So so that's the definition of this link matrix, and that's what Google creates by quote unquote crawling the web, right? It's actually visiting the web pages, parsing out all the information and updating all these sets of links. And the other piece that we will need is the number, right? This ni is going to be the sum over j of lij. And if you think through what this is just the total number of links emanating out from web page I, right? So if I create a web page and I link to the New York Times and to the Washington Post, and that's all, my web pages ni would be 2, right? Because I created 2 links to 2 external pages. And maybe I link myself too, right? If I link to myself, then my ni is going to be 3, right? So in any case, what is, let's kind of get to the punchline here. The punchline is that you want to imagine, and this is what sort of Google imagines, or the paper that proposed this Google's PageRank imagined, is that there is this random surfer process, right? So you're kind of pretend that you're just, you pick the page at starting point, some web page at random, right? You log into your browser, you're looking at some web page, and you at random select one of the links that's on that page, and you move over to you click on it, and now you're redirected to page J. Now you're at page J, you look at you go through its links, pick one at random, and you move over to some random page K, and so on, and you keep doing this over and over and over, right? And so this is clearly a Markov chain, right? So hopefully you can convince yourself that this is obviously a Markov chain, and you can even, here I've written down its one-step transition probabilities, right? The probability that I go from page I to page J is just whether there's a link between I and J, right? This is a 0 or 1 variable. I can't go to something when there is no link there, divided by the number of options that I had to choose from, right? This is the number of links I was presented with, and so that's going to be the probability then. So here you'll recognize that what I wrote, right, with this definition here, all I've written in this equation is the global balance relation for a stationary distribution of this random surfer, right, web surfer process. But for a minute, let's not think about this as a stationary distribution. Let's think about pi j as the page rank of page j. So first of all, again, what is page rank? Just to review, the concept is we want to give some notion of relevancy or importance to a web page, right? If I search, Google right now for, I don't know, maybe current election results, there's going to be a lot of blogs out there that mention those words, right? I want to be presented with, the high ranking, right, pages with high rank, the ones that are somehow relevant or important or influential. And so if we define kind of in our minds right now pi j as the importance, or in other words, the page rank of web page j, how is it computed? Well, it's a sum over all the other web pages. And whenever there is a link to page j from some page I, right, the page rank of page j increases, and it increases in proportion to how important page I is, right? So the idea that you're seeing here, hopefully, is that as if you're running a web page, right? If you're running a web page j, your page rank is going to be high when a lot of high-ranking web pages link to you. Right? So LIJ are the web pages linking to you, your page J, and when their page rank is high, your page rank is going to be high. And now notice that there's another term here, right? The number of links from page I total. And when this number is high, this page rank contribution is going to be somewhat diminished, right? Sort of like if you got a link from some important web page, but that web page seems to be linking everybody, right, then it's, you're not as special, right, so to speak, and so you don't get as much of a contribution. So the notion of this, this notion of relevancy is pretty intuitive, right? And notice we didn't have to say anything about the stationary distribution. It's just sort of, kind of a measure of importance of a certain page, right? And at the same time, it represents what exactly? It represents how often we're going to find ourselves, or this random surfer process is going to find itself, in page J after a long time, right? So clearly, the more often the random web surfing process is going to find itself at page I, the more important, page I is, right, or page J, whatever the index is. So why is this almost good page rank, right? This is this is a typical example given. It's not necessarily all that interesting, but the idea is that when you have these are meant to represent web pages, so you have 3 web pages in this kind of early version of the internet, maybe, right? And so the point is that this is a disconnected directed network. So why is it directed? Is because I have arrows on these edges, right? These are, you could think of them as transitions, and they only go one way, right? In here there's in here they go both ways, but you can imagine sort of a more generic example where there isn't this kind of back and forth nature, right? I didn't have to link, I didn't have to put a link from page 2 to page 1. So in general, right, directed means that you don't necessarily have a link going both ways. But the idea is that there's no way to go for this random surfer process to go from pages 1 and 2 to page 3, right? There's a disconnection here, right? This deals with the concept of irreducibility that we'll cover in the next lecture, and I think you're probably familiar with it from 160A. So for this example, right, I wrote down what the transition matrix is. In this particular case, this also coincides with the L matrix, and you immediately see that you get, kind of 2 stationary distributions, and that, should maybe kind of explain a little bit why this is not the perfect solution. Basically, there's a much more a much better example would be to have like an actual complicated set of relationships between n web pages here, and then page n+1 comes in and it's not yet connected to the others, and now it has this own kind of stationary distribution vector, and you want to include page 3 somehow, but you also don't want to give it a high page rank because it's new. We don't know very much about it, and so that's sort of one issue. And there's also the solution that I'm going to present to you in the next clip, which was the kind of the first of all, it was the original proposal in the Google PageRank paper, but also it relates to this thing called personalized PageRank. So when 2 people search Google, you're not necessarily guaranteed to see the same exact search results, and so I'll show you we'll give you a little bit of detail as to how Google does that. But more importantly, right, if we're talking about reversibility, we may want to ask, is this process reversible or not, and what does it mean if it were, right? Namely, do these local balance relations hold? And I think this goes back to this directed network notion and your homework, right? In your homework, are basically showing that every reversible Markov chain is a random walk on an undirected network. An undirected network is one where these arrows that I've drawn here in this L matrix, whenever there's one in one direction from one site to another, from site I to site J, there's always going to be a reciprocal arrow back, right, from J to I. That's going to give me, if you think about it a little bit, that's going to give me a symmetric matrix L, meaning whenever Lij is equal to 1, Lji is equal to 1, and that's exactly what you have in your homework. And at that point, this random web surfer process becomes reversible, right? And hopefully you see, sort of how this works, right, in the context of your homework, right? And you'll even be able to understand be able to see that the stationary distribution, or in other words, the page rank, is proportional to the number of links on appearing on any web page. And this is not necessarily the kind of what we want, right? we don't necessarily want to give a high page rank to someone who just has a lot of links on their page. But in this reversible world, all links are reciprocated. So the number of pages that you link from your web page are going to be is going to be equal to the number of web pages linking to you, right? And so in this kind of special reversible world, what you have is imagine if I want to link to the New York Times, I can't do that. I basically have to contact them and say, could you link to me as well, right? And that certainly could have been the rules of the internet from the beginning, right? And he would have given a reversible random surfer process, right? And it would have given a stationary distribution or a page rank that's just equal to the number of pages that you link to, right? Whoever manages to collect as many links as possible on their page has the highest Google rank. But that necessarily implies that for every link that you create, you have to get that page to link back to you, right? Which is not necessarily a given. So anyway, the answer to this is no. This is not true in general for the random surfer web surfer process. And in general, this Google PageRank, which is a stationary distribution, does not correspond to a reversible Markov chain. So in the next clip, I'll talk a little bit about what Google actually does. It's a very small modification.